Let us next see division of two complex numbers. Suppose you have two complex numbers. Z1 and Z2 such that Z2 is not equal to 0. Then we define Z1 divided by Z2 by this formula. It is the product of Z1 and the multiplicative inverse of Z2. That is the meaning of Z1 divided by Z2. And this, if you recall, we have already shown what this one is. If Z2, for example, is A plus IB, where A and B are real numbers and this is non-zero, then Z2 inverse is this complex number. A divided by A square plus B square plus I times minus B divided by A square plus B square. Okay, so let us now take two concrete complex numbers and calculate this result of division. Actually we can take anything, but let us see what the authors have taken. Says Z1 is 6 plus 3i and Z2 is 2 minus I. So this means you have to first of all calculate Z2 inverse. Now Z2 inverse by this formula will be what? What are A and B here? A is 2 and B is minus 1. So 2 divided by 2 square plus minus 1 square plus I times, you remember you have minus B here and B itself is already minus 1. So minus of minus 1 divided by this. So what will it be? 4 plus 1 is 5. That means the real part is 2 over 5 and the imaginary part is 1 over 5. I times 1 over 5. Now you have to multiply this complex number and this complex number. So this is equal to Z1 times Z2 inverse and that thing equals 6 plus 3i times this. And now of course our usual complex multiplication. You can do like how you ordinarily multiply two such expressions using the usual rules of algebra, and wherever you encounter I square you have to replace that with minus 1. That way also you can do, or you can use the original definition where we first multiply the real parts and then from that we subtract the product of the imaginary parts, that thing. Okay, instead let us just simply do, we just simply manipulate this algebraically. Oh, by the way, why are we able to do this as if we are working with real numbers? That is because the algebraic rules that the real numbers follow, all those things, commutative law, associative law, the exact same rules the complex numbers also follow. That is why, that's the justification. So 6 times this is 12 divided by 5. Then plus 6 times this is plus I 6 divided by 5. Then this times this is I again 6 divided by 5. And finally the product of these two terms 3 divided by 5 times I square. So that I square will be minus 1. That is 12 over 5 minus 3 over 5. And what happens to this? See, these two terms are the same. So twice of that. That means 12 divided by 5. So this is 12 minus 3 is 9. 9 over 5 plus I times 12 over 5. So that is Z1 divided by Z2 for this Z1 and this Z2. Note that this has been possible because Z2 is not equal to 0. The 0 complex number has both its real part and imaginary part equal to 0. Now let me check if I calculated it correctly. Yes, 9 over 5 plus I times 12 over 5. Next we see powers of the imaginary unit I. Okay, we already know that I square is equal to minus 1. In fact, to have this true, we did all these things. We developed the system of complex numbers just for this. But then again, we are getting extra things also. So, what can we now say about I cube? I cube, of course, by definition is I square times I. However, I square is minus 1. So we will get minus I. Minus 1 times I. So this is minus I. Let us calculate one more power. I to the power 4, which is I square whole square, but I square is minus 1. So this ultimately becomes plus 1. You may be thinking that how long can we carry this on? I mean, higher and higher powers will continue to come. So do we have to just keep on calculating these powers? No, luckily, you already have calculated everything that you need to know. The first power is I itself. The second power I squared is minus 1. The third power I cube is minus I, and the fourth power is 1. Let us see how this much is enough. Consider any integer, say j, okay. J can be positive or negative or 0. J is any integer. J is not a fraction, it's an integer. Then say we divide j by 4. We can do division, and division will produce a quotient and a remainder. We have learned this in school, basic school arithmetic, that you can divide any integer by a non-zero integer to get a quotient and a remainder. Okay, maybe I think in class 2 or 3 we learned this. We get a quotient, and let me give some name to this quotient, say Q, and a remainder R, where there are only 4 possibilities for R, 4 possibilities, and the possibilities are these: 0, 1, 2 and 3. See, the thing is that when you divide something by 4, the remainder can either be 0 or 1 or 2 or 3. It cannot be anything else, and this is true even when j is a negative integer. The quotient can be anything, I mean it will be some integer, we cannot say something like this about q, but that r will be one of these 4 numbers. Hence, and we also know how these 4 numbers are related: j, 4, q and r, and the relation is this: j is equal to 4q plus r. Now, what is the link of this with these powers of I? Let's see. Hence, let us now consider this power of I to the power j, where j is that integer. So let's substitute this expression for j. So this becomes I to the power 4q plus r. Now if you use the usual rules of exponents, you will get I to the power 4 whole to the power q times I to the power r. But you have already calculated that I to the power 4 is 1. So this power vanishes and you are left with I to the power r. Why is this, why is it okay to stop here? That is because depending on what r is, you already know what I to the power r is. If r is 0, then I to the power r is 1, because I to the power is 0. If r is 1, then it is I. Let me write it down, okay. If r is 0, then I to the power j equal to I to the power r is equal to 1. If r is 1, then I to the power j equal to I to the power r is equal to I. Okay. If r is 2, then this is I square, which is minus 1. And finally, if r is 3, then this is minus I, and that's all. Just by calculating 4 powers of I, you have essentially calculated all powers of I, where the exponent j is some integer. If you want to see a concrete case where in place of j you have an actual integer, you can consider this. For example, say I to the power 42. Okay, so the thing is that you have to take apart the part that has 4, like this: I to the power 4 to the power 10 times I square, or whatever we did here, you can do that also. You divide 42 by 4, then that means writing 42 as 4 times 10 plus 2, so the remainder will be 2. So, do you see that in this calculation ultimately the remainder is what makes, what matters. The quotient 10 does not really matter, it is ultimately going to go away from this thing, it will vanish. So, the remainder is 2 and that is why this power is minus 1. Let us see another one, say a negative one, say minus 13. Okay, so you try to write minus 13 as 4 times something plus something. Okay, let me write it like this. Four times minus 4 is minus 16. Minus 16 plus 3 is minus 13. This will be 1 and we are having I cube. So this is minus I. So this way you can calculate any integral power of I. Integral power means where the exponent is an integer, positive, negative, anything. Now before we leave this part, this powers of I, let me again re-emphasize something. And you please try to remember this, okay? It will be useful in future. You did something here and you saw that the remainder of division of something by something is important. The remainder is important. You remember this, okay? There is actually many things behind this remainder being important. You will see later why. Alright, so let us next come to the issue of square roots of a negative real number. Okay, let us raise this question. Let's start like this. We already know that I square is minus 1, and that is why minus I whole square will also be minus 1, because it will be again I square. So the two square roots of minus 1 are I and minus I. For square, let me write SQ. I and minus I. Okay. Why only two? I mean, these two square roots of minus 1 you have found. What is the meaning of square root? It is a number whose square is that number. That number means, if in this case that number is minus 1, so you are seeking a number whose square is minus 1. So that number will be a square root of minus 1. One such square root is I, another one is minus I. Why do we think that there is no other besides I and minus I? Well, that is because we are talking about square root. So that means we are talking about the solutions of a quadratic equation. A quadratic equation can have only two roots, not more than that. I mean, with the things that we are familiar with, in our systems, the systems where we are working, quadratic equations only have two roots. Alright. In some systems they can have more than two roots, but that we do not have to get worried about that. Okay, now if I ask the same question about say another number, minus 3 say, what are, okay, there is something about the notation also. How do you denote the square root of minus 1 symbolically by writing like this? This means, so you see, by definition, since I and minus I are both square roots of minus 1, so this symbol can mean any one of them. However, we have to be definite about what this means, otherwise it will be confusing. So this means I for us. If we want to mean minus I, we will write minus root minus 1. Now the next question is this: what are the square roots of minus 3 say? Let us try this number. Root 3 times I. Let us square it and see what we get. So obviously, what is the meaning of this? This means root 3i times root 3i. I just want to show you something. This is what it actually means, right? This is the meaning of square. But then you can take root 3 and root 3 together and I together and write like this. But why? What permits you to do this? Commutativity of multiplication. Complex multiplication is commutative. That is why you are able to do it. Okay, so now I square is minus 1 and root 3 square is 3. So you are going to get minus 3. Just give me a moment. Okay, so you actually are getting minus 3. So another such number will be minus root 3i. So the square of this will also be equal to minus 3. However, when we will write root minus 3 to mean a square root of minus 3, which one of these two shall we mean? By this we mean this number. If we mean the other number, then we have to write minus root minus 3. Okay, so that is the reason root minus 3 is equal to this. In general, if you do this same procedure, if A is a positive real number, then the square roots of minus a are, so whenever where you had minus 3, this was the one of the square roots. In this case also, it will be square root of a times I and minus square root of a times I by this, whenever you see this, it will mean this complex number. Okay. Now let me show you a calculation which may seem like a paradox at first, but it's not a paradox, of course. You may think that you have got a proof that 1 is equal to minus 1. This type of funny proofs are you can often find circulated on social media, on Facebook. You won't find these things on Instagram, however. You see, this is what you can do, and if you do so, then you will get a wrong answer. So you start with 1, all right? Now 1 is minus 1 square, okay? And that is also equal to, perhaps I am messing this up. Now this is not how it starts. Instead, this is how it starts. We start with minus 1 and write this as I squared. Yes, this is how it starts. Now what is I? I is root minus 1 according to what notation we are using, we have developed here. I is root minus 1. So this means square root of minus 1 times square root of minus 1. So what you do, how you treat real numbers, how you work with real numbers, you take the square root over both the numbers and both of them are minus 1. But minus 1 square is what? 1. And square root of 1 is 1. So you seem to have proved that minus 1 is equal to 1. Obviously that is not true. But then what's the mistake? Where did it go wrong? It went wrong at this step, which is questionable. The usual rules of exponents that you use, one of those rules lets you write, for example, in place of this. However, always keep in mind that this rule works only when the numbers under the radical sign are positive. Well, they can be 0 also, but not negative. Whenever negative numbers under radical are involved, the quantities you are working with are no longer real numbers. So the rules you have always used for manipulating real numbers are no longer true. Okay, so there also if you blindly use those rules, you will get some such absurd results, some nonsense. So this calculation is wrong. So this is where it went wrong. Okay, don't do this. Next come the identities. In our school algebra, when we were for the first time introduced to algebra in school, we got our those formulas, which by now, you can just simply recite them as if you are reciting a poem or something like that. A plus b whole squared equals a squared plus 2ab plus b squared, those type of things. The exact same things are also true in the realm of complex numbers. Let's see how. Suppose Z1 and Z2 are two complex numbers. Then let us calculate this and see what we get. The meaning of this power is this product. And after this, we are going to carry out the multiplication. But in doing so, we will also carefully see which of the properties of complex numbers we are using at every step. Say if I write, after this if I write this, we have used one of the distributive laws. Which one? That one which tells us this. Say A, B and C are complex numbers. Then this equals AC plus BC, the right distributive law. We have multiplied this sum from the right side by this complex number. So Z1 times this plus Z2 times that. At this step we have used the right distributive law which is available to us. At the very next step we are going to use its left version. This equals CA plus CB, the left distributive law which is also true for complex numbers, and that way we can write Z1 plus Z1 Z2. Ideally you have to put brackets. Z2 Z1 plus Z2 Z2. Now next what do you do? Z1 of course is Z1 squared plus Z1 Z2 plus. Now in place of Z2 Z1 you can write Z1 Z2 because complex multiplication is commutative, that is why. Okay. At the very next step you write this. You may be dying to write 2Z1 Z2 here, but what is the justification? There should be some reason for that, no? How can I write this in place of this? Here I have used the fact that complex addition is associative. That is, this is what I have used. A plus B plus C. Think of Z1 squared in place of A, Z1 Z2 in place of B, and this entire thing in place of C. So you can add this B to C together, and to that sum you can add A. If you do so, you are going to get the same thing that you will get here at the previous step. The associative law for complex addition has been used here. Once more you apply the associative law to bring this and this together. And now you can write plus 2 Z1 Z2 plus Z2 square. But what gives you the liberty to lift the brackets? Again, associative law. If you do not write brackets, what happens is that you get two interpretations of the sun. That is, you get this. But what does it mean? Does it mean that you have to add z2 square to this, or does it mean you have to add z1 square to this? It means both. The thing is that associativity tells you that both of them are the same thing. It is this rule that allows you to write things like this, so that if you add these two together first, and that way you calculate the sun, you get one thing. However, instead of that, if you add these two together, that way also you get the same sum. That is why we do not write bracket without causing any confusion. And you are getting back your usual formula, a square plus 2ab plus b square. So for complex numbers also those same formulas, not just this one, the other ones also are true. For example, these formulas are true. This part may seem like a very long calculation which has been made intentionally long, unnecessarily prolonging it, unnecessarily lengthening it. But you see, simply because you have become so familiar with the laws of arithmetic that they are very natural to you, that you skip 3 or 4 steps and you just simply write this. That does not mean that if you be careless, you will always be saved. There are some places which are unfamiliar, which will be unfamiliar to you. There you cannot hope to be so quick unless you know those rules very well. Okay. We have lived in the arithmetic world of these ordinary operations for so long that they have become so natural that we do not really want to investigate the steps. But the other worlds that lie out there, their things are different. So the other identities, of course, one of them is this -2 plus z2 square. Then you have another one for cube also, z1 cube plus 3 z1 square z2 plus 3 z1 z2 square plus z2 cube. You can similarly verify these things. -3 z1 square z2 plus z1 z2 square minus z2 cube, and this fourth one, like the a plus b whole squared, is also a famous one or infamous, depending on how you look at things. And whatever other formulas you may be familiar with from your classical algebra, that is school algebra, continue to be true here. Why? Well, the reason is simple. The rules that the arithmetic of real numbers follows, that exact same rules the complex numbers also follow. That is why. Same commutativity, associativity, those things. Okay. Let us now next see this example. express the following in the form a plus bi or a plus ib, same thing. The first one is I times minus 5i times 1 over 8i. Okay, so let us first do this one and then we will see the second one. There is another one. I times minus 5i times 1 over 8i. So of course this is minus 5 over 8 times 3 i's are there, so I cube. Moments ago you calculated that I cube is minus I. So this is 5 over 8 times I. Let's see the next one. Here you have minus I times 2i times minus 1 over 8i whole cube. Minus I times 2y so we can simplify things by considering this minus I square. Okay, so these two i's we take together. Because we have minus and cube, so minus will remain I cube divided by 8 cube. Okay. I square is minus 1, so minus I square is 1. That means this does not have any effect. You will, you see, I cube is minus I, that minus and this minus will give us plus I. And below what do you have? After cancelling a 2, you get 4 times 8 times 8. That is I over 256 or 1 over 256 times I. Okay, so this way you can simplify things. Oh, we had, okay, hold on. We had to express it in this form. So that means I cannot simply write this. I have to write 0 plus 5 over 8 times I. Similarly here also 0 plus 1 over 256 times I. I don't know if I did some kind of mistake in taking down part 1. I think this is not what the book tells us. The book tells us something else. But now I don't really know. Okay. I think this is not what the book says. It is something else slightly different. But anyway, if it is this expression, then it turns out to be equal to this. Let's see another one. Express five minus 3i cube in the form a plus ib. So you can apply your formula, that identity, but be careful, there will be powers of 5. Okay, so 5 cube minus 3 times 5 square times 3i plus, after minus we have plus. Oh, and one more thing, if you do not really remember these formulae very well, say you are not confident about what the expansion is, you can always do ordinary multiplication. No, you write 5 minus 3i's and then you just multiply them. Plus 3 times 5 times 3i square minus 3i cube. So 5 cube is 125. Then what will happen to this one? 9 times 25. No? I have a problem. The problem is that I cannot do calculation mentally. Unless I write things down, I cannot do anything. Okay, that is my problem. So this becomes minus 225i. What will happen to this? 3 times 3 is 9, 9 times 3 is 27. Simple things I can do, but if it goes to 3 digits or 4 digits, I cannot do that. I cannot even do addition or subtraction, forget about multiplication. (135), and there will be I squared, so minus 135. And finally, I cube will be minus I, and we already have a minus, so plus I and 27i. So what are we getting? Minus 10 and minus. So if you do the calculation, (225) minus 27 minus 198 I. Okay, so you can imagine what a nightmare it is for me to write exams, because I take a long time to do even this type of calculations. It was nightmare, it's not anymore, that's a different thing. So this is our complex number in a plus ib form. Let us see this another one. Express minus root 3 plus square root of minus 2 times 2 root 3 minus I. In the form a plus bi. The part here that may confuse you initially is this root minus 2, but recall root minus 2 is root 2 times I. Okay, so now let us do the multiplication. First, this times this gives you what? Root 3 and root 3 will give you 3. 3 times 2 is 6 and there is a minus sign, minus 6. Then root 3 times this, minus root 3 times minus I. So plus root 3i. Then this times this. So it will be plus 2 root 6i, and finally root 2i times minus I. Minus I square is minus of minus 1 plus 1. So plus square root of 2. That is root 2 minus 6. That's the real part, combining these two real numbers, and the purely imaginary number. If you want, you can take root 3 common out. That way you will get 1 plus 2 root 2 I. Okay, so this is the number in the form a plus bi. Let me check. Minus 6 plus root 2. Yes, this is the one. Okay. Next, the modulus and conjugate of a complex number. Associated with each complex number is something called its modulus, and again another thing called its conjugate. I need a bit ink. The syllabus is unrealistically large and there are many unnecessary things, which is why we cannot enjoy these things. Had there only been a few chapters, we would have enjoyed the chapters. If you are of the impression that these things are really just some mathematical curiosities, yes, they are. But if you think that they won't have any applications in the real world, then you are wrong. The name complex numbers, especially the name imaginary unit, gives the impression that it does not exist, whereas real numbers exist. That's not true. Complex numbers have as much existence as real numbers have. But the more surprising thing is that they are in fact applied in physics as well as in in many places actually, electrical engineering as well. Let this be a complex number, where it's of course understood that A and B are real. A is the real part and B is the imaginary part. The modulus, or there is another name, absolute value of the complex number set, denoted by this. We denote the modulus by writing vertical bars on both sides of Z. is defined as this. You take the square root of the sum of the squares of real and imaginary parts of the complex number. This is a real number, and this real number is called the modulus of z or the absolute value of z. Note that is a non-negative real number, i.e. this is greater than or equal to 0. So the complex number itself can be any complex number, but this is its modulus is a real number, and not just that, it is non-negative. It is not negative. It can be positive or it can be 0 also. It becomes 0 in that only one case where z itself is equal to 0, where both a and b are 0. And then there is complex conjugate or simply conjugate. The complex conjugate or simply conjugate of the complex number z. This one also has a symbol for it. It's denoted by z bar. Over z you put a bar. Is defined as this. That is, if your original complex number is a plus ib, then its complex conjugate z bar is a minus ib. So to get the complex conjugate, you change the sign of the imaginary part. If the original imaginary part is b, now you write minus b. You do not do anything to the real part, that remains a. Okay, so that is complex conjugate. For example, say you consider the absolute value or modulus of the complex number 3 plus I. By definition, it is square root of 3 square plus 1 square. That means 9 plus 1, 10. Let's see another one. 2 minus 5i. What is the real part here? 2. Imaginary part is not 5. It is minus 5. And also imaginary part is not 5i. The I it is not a part of the imaginary part. So 2 square plus minus 5 square. Minus 5 square is 25 and this is 24. 4. So square root of 29. You can see that these are all positive real numbers. And yeah, that's it. And let us next see some complex conjugates. The complex conjugate of 3 plus 2i, 3 plus I. If you want, you can use brackets, or you can just simply take the bar over the entire complex number. What is the imaginary part here? 1. In place of that, you write minus 1 and get the complex conjugate. What's the complex conjugate of 2 minus 5i? The imaginary part here is minus 5. You change that to plus 5. Let's see another one. Minus 3i minus 5. What is the imaginary part of this complex number? It's not minus 5, it is minus 3. You change that to plus 3. The rest remains same. Okay, so that's how you have to take complex conjugate or conjugate. Alright, let us now link a complex number, its absolute value, that is modulus, and its complex conjugate. These are linked together by a relation. Let this be a complex number. Then let us consider this. The square of the absolute value. What is the absolute value or modulus? Root a square plus b square. So its square will be a square plus b square. Now if you look carefully, this is a square minus I square b square. Because I square is minus 1, so that will give us plus. However, using that formula, z1 square minus z2 square equal to z1 plus z2 times z1 minus z2, you get minus bi. So a plus bi is your original complex number, whereas a minus bi is its complex conjugate. And you have got this nice relation that the square of the absolute value is the product of the complex number and its complex conjugate. Okay. Now, say additionally your complex number is non-zero, it's not equal to 0. Suppose this is not equal to 0. Then we saw before that whenever a complex number is non-zero, its multiplicative inverse exists, z to the power minus 1. It exists in C. Now, what will happen if we multiply both sides of this equation by that z inverse? The left hand side, of course, will be this, and the right hand side will be this. Okay. What is z inverse z? It is 1. Now, because your complex number is not equal to 0, let us just see one thing. What can you say about its absolute value and its square? Since z is not equal to 0, either a is non-zero or b is non-zero. Because if a and b are both 0, then z will become 0. So, a square plus b square is not equal to 0. Because a square plus b square can be 0 in only one case, when both a and b are 0. and a square plus b square is this. So that means this real number is not equal to 0. So you can divide both sides of this equation by this real number. If you do so, what will you get? So you have got a formula for calculating the multiplicative inverse of a non-zero complex number in terms of its absolute value and complex conjugate. Let us use this formula, on this complex number and see what we get, because we already know what Z inverse is. Are we going to get that same thing? We should get. Let us see if that happens. So our complex number is a plus ib. So its complex conjugate will be a minus ib. And what is this? A square plus b square. If you write it in the form something plus I times something, you are getting this. So yes, you see that you are actually getting back your original Z inverse, the multiplicative inverse. Okay, so using this formula also you can calculate the multiplicative inverse. Now this absolute value or modulus and complex conjugate, they have some properties. And these properties you can verify relatively easily, but if you see the properties that now I am going to write of these two things, you should be able to prove them. But if you cannot, you write in the comment section below. Okay, and here Z1 and Z2 are two complex numbers. The first property is this. The product modulus of the product is equal to the product of the moduli. The second property is this. Modulus of this quotient is equal to this, provided of course that Z2 is not equal to 0. Then there are these involving the complex conjugate. I don't know if I should, well, it's actually not given in the book, but let me just anyway mention it. If you take complex conjugate 2 times, you get back the original complex number. Then the complex conjugate of a product is equal to the product of the complex conjugates. The complex conjugate of some, it's given in a very confusing manner in the book. They have written plus and minus together, which may be confusing sometimes. So let me separately write the 2. Minus Z2 bar. All of these properties are very easy to prove. Maybe the ones involving modulus will be somewhat complicated, but again I told you that if you do not get them, then write in the comment section below. And finally, the complex conjugate of this ratio is equal to the ratio of the complex conjugates, provided that Z2 is not equal to 0. And before we stop the video, let us see two more examples. With that, actually this section ends. Section ends means there are other things also after this, but this one ends, and we will then solve exercises. Find the multiplicative inverse of 2 minus 3i. Okay, so let us use that formula which involves complex conjugate and modulus. Two minus 3i inverse is, by that formula, it is first of all the complex conjugate of 2 minus 3i divided by the square of its modulus. Square of modulus, okay, remember that, not simply modulus. To calculate the complex conjugate, you change the sign of the imaginary part, so it becomes 2 plus 3i. And what is this? 2 square plus minus 3 whole square. So 2 square is 4 and 3 square is 9, minus 3 square is 9, that means 13. Plus I times 3 divided by 13. You can actually do something else also here. If you see an alternative method, essentially this is what you are trying to calculate, right? What you do, you multiply and divide by the complex conjugate of this. That is 2 plus 3i and 2 plus 3i. This, if you use that formula, a plus b times a minus b will eventually give you the same thing. Okay, so it's up to you to do in whichever way you want to do it. Let us see another example. Same thing, x. Same thing means not multiplicative inverse, but we have to express in a plus bi form. Number 1, 5 plus root 2i divided by 1 minus root 2i. I will just give you the hint. You do this. That is, you multiply and divide by the complex conjugate of the denominator. You did something similar in school, no? I mean in lower standards, where you multiplied and divided by just how you rationalized denominator when you worked with irrational numbers. The similar thing here we are doing, realizing numerator, making it real. There you, denominator. There you rationalized the denominator. So you made the denominator a rational number. Now we are making it a real number. 1 plus root 2i, 1 plus root 2i, and then you do the calculation. The denominator is in the form a minus ib times a plus ib. So that will turn into a real number, and you do the numerator multiplication and finally bring it to the form a plus bi. Okay, so this is your, if I say, homework. And there is another one. How shall we simplify this power of I? Again, recall what we did there. We divide minus 35 by 4. What is the nearest you can go to minus 35 using multiples of 4? Minus 36, because 4 times 9 is 36. You can write minus 35 as minus 36 plus 1. Now in place of minus 36, you can write this, because 4 times minus 9 is minus 36 times I to the power 1, which is I. So this is nothing but I, because this one is 1. And with that, this section theory part is over. So in the next video on complex numbers, we are going to solve the exercises. And tomorrow, if I am remembering correctly, we again have commutative algebra. Anyway, we will see what it is. So that will be all for tonight. So see you tomorrow with commutative algebra or whatever is there in the schedule. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.